Today's lesson is a continuation of the topic binary ionic compound nomenclature. In today's lesson, it will be very much like ionic compound nomenclature type 1, except for the metal or the cation will have more than one possible charge value to it, and therefore will need to be named slightly differently. In today's lesson, you're going to see what these little Roman numerals are going to mean. The Roman numerals are pretty much going to be just a way of saying the identity of the metal. For example, if there are two people in our class, both with the name Billy, I might need to call the first one Billy W, while I might need to call the second one Billy S, based on their last name because they have different identities, so we can identify who is who. Same thing for metals that have more than one possible charge, so that we can name them appropriately. We will then go through our Inkscape simulation and show you how you can write the formulas from names, and then finally we'll show you how you do the names from the formulas. Okay, we're back at our simulation, and again what you will notice is we have a grouping of cations over here and some anions over here, and we're going to put them together like we did in the previous lesson. What you will notice though that's different here is that I have two versions of copper. For example, you'll see that I have a Cu with a plus. This is going to be called copper Roman numeral 1, or just copper 1, identifying it as copper that has a 1 charge, whereas this guy here will be copper Roman numeral 2, or also known as copper 2, because he has a +2 charge, indicating that these are two different coppers that have different structures to them, and because of that they're going to bind differently to other elements. For example, if we have copper 1 and it has an option to intermingle with, let's say, oxygen, what we would see here is that the ratio does not work out on a simple 1-to-1 ratio because there's only a +1 charge for the copper while there's a 2- for the oxygen. So there's not enough positives to cancel out the two negatives of the O. So I would actually need another copper to do this. So what I would need here if I was using copper 1 in oxide is that I actually need two of them. So my formula for copper 1 oxide, this sounds a little bit weird, but copper 1 oxide is actually going to have the formula Cu2O, meaning it has two coppers for every one oxygen, or better stated, two copper 1s for every one oxygen. Okay, so this is going to be copper 1 oxide. Now, if I want to form copper oxide, but with copper type 2 or copper Roman numeral 2, what we would see here is that I have two positives, and if I bring the oxygen, which always has two negatives because these don't vary, these would simply piece together easily. So when we look for copper 2 oxide forms in a different ratio. Because of its +2 charge, we only need one oxygen to cancel it out, and we have a 1-to-1 ratio here. This formula would be CuO. This would be the formula of copper 2 oxide. So copper 2 oxide is CuO, whereas copper 1 oxide is Cu2O. Very important to notice that the difference in these charges makes the compound that's formed different. So we have to recognize what the name is and write the formula accordingly. Alright, I'm going to move these guys off to the side. We'll do one last little quick example because I always like to do 3 examples. And let's say, for example, that I use Fe with a 3+. Now, there are two versions of iron that are out there. Okay, there's iron 3 and there is also iron 2. Okay, iron 3 means that it has a +3 charge, so therefore this guy must be iron 3. So if I wanted to combine iron 3 with nitride, okay, again nitride because of the IDE ending of an anion, they form nice in a 1-to-1 ratio. I would need one iron 3 for every one nitrogen, and as you would write the formula, we see it's 1-to-1 ratio. The formula would be Fe(N). This would be the formula for iron 3 nitride. Now if we had an iron 2, now I don't have it in the simulation, but if I had an iron 2, it would have meant that the iron would have had a +2 charge and it would have resembled the shape of copper. And if I paired that up with nitrogen, they wouldn't have fit in well. So the formula would have been different for iron 2 than it would have been for iron 3 nitride. So we must keep in mind that when we're using these formulas, the Roman numeral is incredibly important because it will determine the formula that we are going to write. Okay, so finally, again, why did we use Roman numerals? Well, again, the Roman numerals are used when you have more than one identity for the metals. These metals are generally going to appear in your transition metal section. On our periodic table, I have a little box that will indicate which ones have multiple personalities, so we would recognize them. But what we would see here is that the Roman numerals are used to explain who they are. For example, Cu plus or Cu2 plus are both possibilities for the copper ion. If we notice copper with a +1, the way we will notice write it will be copper 1. If it has a +2 charge, it'll be copper 2. Very simple. The Roman numeral is the charge value. Okay, so for example, if we used Sn2 plus or Sn4 plus, the 2 plus is just tin 2. The 4 plus is tin 4. And likewise, if we look at iron, iron has two possible identities, 2 plus and 3 plus. So therefore, it has to have two names. Iron 2 or iron 3 are both sufficient. Now there is another older way of naming these particular ions. We're not going to look at it in this lesson, but we will in class at a later point. But right now, you just need to recognize that the Roman numerals will be the actual charge values. Finally, the harder part of this lesson for most people is how to get the names from the formulas. The way you need to do it is kind of through scratch work. For example, this CuCl2, a lot of people might think that this is copper 1 because there's a 1 next to the copper. But again, remember, the Roman numeral does not specify the amount that you have. It specifies the charge. Now, if we were to do our scrap work, the Cl has a -1 charge. And if I have two of them that have a -1 charge, that means overall I have two negative charges. So this one copper here has to cancel out the two negatives. Therefore, that's why it's copper 2, because it needs a +2 charge in order to balance out the two negatives of chlorine. It's a little bit of mental algebra there. You might come up with your own technique, but however we do it, you just have to feel comfortable with it. All right, we also notice for iron bromide, we see that it's iron 3 bromide. Again, not iron 1, because it doesn't count the ions, it counts the charges. So if we looked, bromine has a -1 charge on the chart. If you have three of them, that means you have three minuses. So you must have three positives in this one iron atom in order to cancel it out. That means that it's iron +3 or iron 3 bromide. If we look at the final example, we see sulfur has a -2 charge according to our periodic table. But there are two coppers here in order to cancel out that -2 charge. So if they split that job of canceling out the -2, then there would have to be two +1 charges for this copper. So if they both had a +1 and there were two of them, that gives me two positives. Two positives cancel out two negatives. That means the identity of this copper was copper +1. So therefore it's called copper 1 sulfide. A little trick, doesn't always work, but generally works pretty well, except for in those cases where numbers have been reduced, is that the Roman numeral is quite often the actual number that was on the anion. So, and again, it's not 100% true, but often it works. So we see that this is copper 2 or iron 3 because of these numbers here. Again, not the best way to go, but if you're really, really stuck, it's a little shortcut that will get you right most of the time. All right, please make sure to check our notes and take the necessary online quiz that are on my website. And again, we will discuss this in more detail in class.